Welcome to the TOEFL Listening section. In this section, you will listen to an academic lecture and then answer questions about what you heard. You may take notes while you listen. You will have time to review your notes before answering the questions. Listen to part of a lecture in a university class. You will hear the lecture only once, so listen carefully. After the lecture, you will answer some questions about what you heard. Some questions ask about the main ideas and supporting details. Other questions ask you to make inferences or connections between ideas. Answer each question based on what is stated or implied in the lecture.
Good morning, everyone. Today we will focus exclusively on how hurricanes form and how early tracking determines their initial paths. I want you to think of a hurricane not as a single event, but as an organized system that develops through several identifiable physical processes. First, we need a seed disturbance. In the Atlantic Basin, the most common seeds are African easterly waves. These are areas of enhanced convection and low-level vorticity that move westward off the African coast. Over warm water, they can consolidate into a coherent low-pressure region. A second prerequisite is sufficiently warm sea surface temperatures. In practice, a threshold of roughly 26.5 degrees Celsius over a depth of several tens of meters provides the heat and moisture needed for sustained convection. Warmer temperatures increase the available moist static energy and thus the potential intensity. Equally important is the presence of mid-level moisture. Dry air in the mid-troposphere suppresses deep convection by promoting entrainment and evaporation of cloud cores. Without a moist environment, convective bursts die out and the disturbance fails to intensify. Rotation must be present. The Coriolis force imparts spin, so organized cyclonic circulation can develop. This is why tropical cyclones rarely form within about 5 degrees of the equator. The Coriolis parameter is simply too small there for the aggregation of vorticity into a single vortex. Vertical wind shear is a controlling factor. Strong shear tears apart the vertical alignment of the developing system. Low shear allows the column of convection to remain stacked around the center, which is necessary for intensification. Regions of low shear are therefore fertile for hurricane formation. Energy conversion is central to this process. Moist air rises, water vapor condenses, and latent heat is released. You can think of the latent heat released by condensation as the fuel that powers the storm. That heating warms the core, lowers central pressure, and strengthens the inflow and outflow. When a nascent vortex becomes well organized, it goes through stages. We talk about a tropical disturbance evolving to a tropical depression, then to a tropical storm, and finally to a hurricane once maximum sustained winds cross the threshold of 64 knots. Intensification can be gradual or rapid depending on the thermodynamic and dynamic environment. Rapid intensification is a topic of current research. It often requires very warm sea surface temperatures, low wind shear, high ocean heat content, and a moist middle troposphere. A clear example is Hurricane Patricia in 2015, where extremely warm water and low shear allowed an explosive increase in wind speed over a short period. A complementary example from the Atlantic is Hurricane Katrina in 2005. It began as a tropical wave off Africa and later intensified rapidly in the Gulf of Mexico, where sea surface temperatures were high and shear was modest. This illustrates how both the sea disturbance and the ocean environment must align. Structural changes such as eye wall formation are important. The eye wall concentrates the strongest convection and the lowest pressures. Sometimes an eye wall replacement cycle occurs, where a secondary eye wall forms and chokes off the inner eye wall. This can temporarily weaken the storm, even if environmental conditions remain favorable. Now, a brief note on tracking during formation. The storm motion is governed primarily by the large-scale steering flow. Subtropical ridges steer many hurricanes westward. Interaction with mid-latitude troughs can cause recurvature to the north and east. Local beta drift also introduces a slow northwestward component in the absence of strong steering currents. Observations are critical to diagnosing formation. Satellite microwave imagery reveals the development of a coherent, low-level circulation and convective organization. Aircraft reconnaissance provides direct measurements of pressure, wind, and thermodynamics inside the developing cyclone. Numerical models assimilate these observations to predict genesis and track. In summary, hurricane formation requires a sea disturbance. Warm sea surface temperatures generally above 26.5 degrees Celsius. Adequate Coriolis force away from the equator. A moist mid-troposphere and low vertical wind shear. The conversion of latent heat during condensation is the mechanism that powers intensification. Tracking then depends on the surrounding steering flows and interactions with larger-scale patterns. That concludes the lecture. We will now apply these concepts in a case study exercise where you will analyze environmental fields for a potential genesis event.
Listen again to part of the lecture, then answer the question.
You can think of the latent heat released by condensation as the fuel that powers the storm.
This concludes the listening section. For more TOEFL practice tests and study materials, visit Spinta.org.